Well, welcome to physics class, and let me talk to you a little bit about where we're going with this, and then we'll start into it. There's quite a few slides in this particular section. What I'm trying to do is to hit 4 chapters by the end of the year, and so we're going to hit them a little differently. I'm not planning on doing any tests. I have it listed in my lesson plans as a summary, and maybe it'd be like an open book test or a review page you turn in, something like that, but not an actual test because I don't want to take the time to pause and do lots of review and do as much emphasis as that I would do normally when I'm teaching it. Just want to hit some highlights. So magnetism, electromagnetism, and charges specifically. We talked about magnets in general in 21A, and the 21B, and we're going to hit a little bit of C, deal with electromagnetism and charges, electricity and magnetism. So a magnetic force on a moving charge. And this is something that kind of came out in, I think 1700s. I don't remember the date on it. A current-carrying wire can produce a magnetic force that can attract or repel a magnet. This actually was discovered because a scientist was working with compasses, and he had a wire on the table that was carrying current, and he noticed that the current in the wire was actually affecting the compass. And then that's where they started to make this connection between electricity, current-carrying wire, and magnetism. And magnets can also affect electrical charges. So electricity can affect a magnet, but a magnet can affect electricity if and only if they are moving. So this is important. Magnets affect moving electrical charges. Okay, so a few observations about this. Number one, a point of charge of either polarity at rest in a magnetic field experiences zero force. So if a charge is not moving, then it will experience no force. The magnetism will not affect it. So a stationary charge is not affected by magnetic forces. So if you go to your review page, I can send home the review page for you. We actually did some of it in the video yesterday also. I want to do number 2, concepts. Number 4, question is, what happens to a stationary charge in a magnetic field? And if it's stationary, nothing happens to it. It's just stationary. No, there's no force on it. All right, second observation. A charge of either polarity that moves parallel to magnetic field lines in either direction experiences zero force. So if it's moving parallel to the magnetic field lines, we did talk a lot about magnetic field lines, okay, but the idea is if it's moving parallel to the magnetic field, then it experiences no force also, okay? However, if any point moves so that it crosses a magnetic field line at an angle, there is a magnetic force exerted on that charge. So this is key. If it's moving at an angle to the magnetic field lines, then it will experience a charge. Okay, technically 0 degrees is an angle, okay, but that's parallel, so don't count that. The magnitude of the force is proportional to the speed of the charge and a function of the angle which it crosses to the field. So how much force is on this charge depends on how fast that charge is moving and the angle also, because obviously the key is it's the perpendicular velocity, so we involve the angle in it. Okay, so it's interested in the angle. It tells us how much of the velocity is actually perpendicular, how much of the speed is perpendicular, and then how fast it's going. And the faster it's going, the greater the force on it. For a given relative speed between the charge and the field, okay, so for a given speed, the force is maximum when the charge's velocity is perpendicular to the magnetic field lines. Okay, because it makes sense. If it's perpendicular, all of the force is going to be exerted on it. If it's parallel, there's no force. Perpendicular is going to be maximum force. Okay, so concepts number 5. This is on your review page. Check your review page. What happens to a moving charge in a magnetic field? And it is going to experience a force perpendicular to both the magnetic field and its velocity. We didn't actually talk about that yet. Sorry, I put that in a little early. Proportional to the strength of the field and the velocity perpendicular to the field. So it depends. How strong the field is important, and then how much velocity there is also important. And it's get perpendicular velocity. All right, we'll come back to that perpendicular stuff in a moment. I should have put that in a different spot in the slideshow. Oh well. The force on a moving charge is proportional to the density of the magnetic field lines or the magnitude of flux density. So proportional to how strong the magnetic field is. And we already said that in the review question a moment ago. Magnetic field, how strong the magnetic field is. And the direction of the force vector depends on the polarity of the charge. Positive and negative will be affected differently, which we'll talk about here in just a moment. Okay, so the magnitude of the magnetic force, not the direction, just the magnitude, is equal to the absolute value of the charge times the speed times the strength of the magnetic field times the angle, a sine of the angle. And that theta is the smallest angle between the velocity vector. Sorry about that. Theta is the smallest angle between the velocity vector and b. Okay, so just process here. So the magnitude of the force is equal to the charge. We're not worrying about which directions. We don't care about the magnitude here. We only care about the magnitude here. The velocity, that's actually speed there because there's no vector sign. The magnetic field strength and the sine of theta. And theta is the angle between the velocity and the magnetic field. Okay, so you have a math question. This is number 2. We're skipping number 1 for the record, and we're doing number 2. So the magnetic field exerts a force of 2.3 times 10 to the negative 7th newtons on a negative 6.40 millicoulomb charge, initially moving perpendicularly to the field at a constant speed of 5.50 times 10 to the second meters per second. What is B? So we have our equation. We plug in our numbers. We have the force there is 2.3 times 10 to the negative 7th newtons. We have the charge. I changed it to 10 to the negative 3rd coulombs because those were millicoulombs. Meters per second on the speed. We don't know B, and then sine of theta. Now we'll just warn you, sine of theta is 1, so that's just going to disappear. And we're going to do some algebra and rearrange it. And that looks really confusing, but if you stop and think through it, that is just rearranged. And we get a magnetic field of 6.53 times 10 to the negative 8th, and that would probably be in Teslas. I believe that would be in Teslas. Okay? So 2.30 times 10 to the negative 7th divided by the other two numbers. Again, the algebra is fairly straightforward. Y'all are smart. Okay, so magnetic force on a moving charge. And continuing. The force of a magnetic field on a moving charge is perpendicular to both the magnetic induction vector and the velocity vector of the charge. Okay, I actually included that in the earlier review question. It's always perpendicular both to the velocity and the magnetic field. So here are some pictures, and we're going to use some symbols here. Okay, let me give you this information just so we got it. Okay, so here we have it. If you look at the one in A, okay, this is a positive charge, and you'll notice the positive charge is moving to the right. The magnetic field is going like into the screen, and the force on it is up. So if you try, as this charge is moving to the right through the magnetic field, it's going to be shot upward. So it's going to curve towards the top of the screen. The left-hand picture, I guess I should have clarified which one I was dealing with there. That was the right-hand picture actually of A right-hand diagram. Okay, velocity is going to the right, magnetic field is going into the screen, and the force is upward towards the top of the screen. In the left-hand picture is the same situation. You got a positive charge moving to the right. The magnetic field is towards the top of the screen, and the force is coming out of the screen. And the way you know the force is coming out of the screen is that circle with a dot. That's the front end of an arrow. If you're looking at this, the arrow is pointing at you, and if an arrow is pointing at you, all you see is the tip of the arrow. Okay? So the arrow is coming out at you. Now you're going to talk about how we know which direction it's going to be going in just a minute. The right-hand side is a negative charge. So in the left-hand diagram, the negative charge is going to the right. The magnetic field, that's B, is going straight up the screen, and the force is into the screen. And the way you know it's into the screen is that little circle with the cross. Those are the feathers at the end of the arrow. If you played with regular arrows, not diagram arrows on a computer, they've got feathers on the end and they make kind of that cross. So that cross is the feathers going away from you, so the force is going into the screen. Or on the one on the right, they try to make it three-dimensional, so the velocity is going to the right, the magnetic field is actually going into the screen, and then the negative charge will be forced down the screen. Okay? So how we know about this is what's called the right-hand rule. The force vector is always perpendicular to the plane defined by B and V. And the direction of F mag on a positive charge can be found by a right-hand rule. Okay, so this works specifically for positive charges, and it's called the right-hand rule. So you hold your hand like they're showing you there, okay? And you take your thumb and put it on the velocity. Take your forefinger, your pointer finger, and run it towards the magnetic field, and then your middle finger at 90 degrees to those two is going to be pointing straight out at you. And because it's pointing out straight at you, you have that little dot there. We're ignoring the angle, and we're just going to perpendicular side. Now, I will tell you, this is really kind of cool. Number one, make sure you use your right hand, not your left hand, because otherwise you'll mess up. And there's a story that I heard about a scientist who was from a European country, and they use left-handed rules here instead of right-handed, and that was true for X, Y, and Z coordinates and all of this kind of stuff. They use left-handed rules. And he did some major science work, and nobody could understand it because everything was backwards, and it confused people. Okay, so on the review page, I asked you to, this is concepts number 6, illustrate the use of the right-hand rule for a charge moving in a magnetic field. And I just duplicated the pictures, but we go back to those first pictures that we had. If you follow this right-hand rule, so put your thumb on the green arrow, this is on A, put your pointer finger towards B. And this works with both diagrams, and you'll get F pointing the direction that it shows there. That's how you know which way F goes. Now in B, you'll use your right-hand rule, but it'll go the opposite direction because that's a negative charge. Right-hand rule works for positive charge. If it's a negative charge, it goes the opposite direction. Okay? I hope that makes sense to you. It's kind of a neat thing you've got on your hand. You've got this you've got this three-dimensional pointer system on your hand. Now, they talk about a number of things, but they talk about velocity selectors, which are kind of fun. This comes from this. What happens when both an electric field and a magnetic field influence a charged particle? So a charged particle is going to be affected by electric field, but it's also going to be affected by magnetic field. Well, of course, the net force on the particle is going to be the sum of the two forces. So how much force there is on it depends on both the magnetic field force and the electric field force. And a velocity selector uses the arrangement of these fields and forces. And what they're trying to do is to adjust the velocity and the fields so that a charged particle passes through undeflected net force. And this allows you to determine exactly how fast that electron is moving, because you know the magnetic field, you know the electric field, you know the forces on it, and you can tell by that how fast the object is, the particle is going, because of course the magnetic field depends on the velocity. Let me show you here some equations. So the total force on the electron, or on the particle, the charged particle, is the electric field plus the electric force plus the magnetic force. The electric force is the charge times the electric field. That's from an earlier chapter, I believe, that we didn't necessarily emphasize. And the magnetic force is the charge times the velocity times the magnetic field. We're assuming perpendicularity here, so we have no sine of theta. And we want it so that the total force is 0 so that the particle goes straight through without being deflected. And so cancel out the q's, because divide everything by q, and rearrange, and you get the electric field divided by the magnetic field equals the velocity. And that's kind of cool, because then if you know the electric and magnetic fields, you know exactly how fast this subatomic particle that you can't actually see is going. So, question number 3. A velocity selector has a magnetic field of that and an electric field of that. What velocity does it select? Well, we have an equation. Plug in our numbers, run it through our calculator. Wow, that was hard. And you get 6 million meters per second, 6.43 million meters per second. So this is truly just plug and chug, okay? All right, let me just do a little bit from 21C, electromagnetism and conductors. Experiments have shown that the force a magnetic field B exerts on a wire segment of length L carrying a current is ILB sine of theta. Now remember, before we had QV, Well, QV works out to the same as IL, because I is the current, coulombs per second, and the length is how far it's going, and it works out to charge times speed. So it's equivalent. I'm not going to justify all the math, but I think hopefully you can kind of see how that would work. So for magnetic force on a conductor, the right-hand rule still works. You put your thumb down the current, because that's where the velocity is effectively. So the thumb still goes on the velocity, but now we're talking about a wire, so it's a current. Your pointer finger along the magnetic field again, and then your middle finger will show you which direction it's being forced. So if you run current through this wire, it's literally going to get shoved down out of that magnetic field. So, illustrate the use, this is number 2 concepts, number 7 on your review page. Illustrate the use of the right-hand rule for a wire with a current. And there you go. That's the illustration I just had, but that's about the best as I can come up with to explain it. If I were to give you a wire and a magnetic field, then you'll use your right-hand rule to determine which direction the force is going to go. Okay, this is kind of interesting. I'm not going to do a lot with this, okay, but I just want to mention it to you. Conductors in the shape of a loop must somehow move within a magnetic field, because if you've got a loop and you've got current going through that loop, one part of the loop is going to be forced down and one part of the loop is going to be forced up. And this is a Bob Jones PowerPoint, of course, and they say this is illustrated by a square loop on page 492. I don't know why they didn't bother to copy it from the textbook into the PowerPoint, but I didn't either because I didn't want to take the time to do that. But this still works. There's torque involved, and because there's torque, because you've got one force on the pushing it down and one force pushing it up, and so it's going to spin. And there is a torque rule. This way they do the torque rule. You put your you put your hand one direction, then you curl your hand towards the other one. And this is a different way of doing right-hand rule. Don't worry about that. But what I did want you to know is this is how a DC motor works. When current flows through the motor circuit, the coil begins to rotate, and the commutator permits continuous rotation of the motor in one direction. So it's a little fancier than this. Okay, I'm not going to get into the details of it, but the basic principle of a DC motor is the fact that you have a magnetic field and an electric current, and then you've got a loop of some kind so that you have pressure up and down on it, and that causes it to spin. So motors are built around this concept of electricity and current electricity and magnetism. Okay, so which direction is the positive charge going to move? I didn't tell you what direction it was going. There we go. Now we've got the direction on it. So text me the answer. Which direction is the positive charge going to move? It's going to be going, just tell me which direction it's going to move, and I'll be interested in seeing your answers. All right, well, folks, have a good day, and we'll talk again tomorrow, actually.